So welcome back, everybody, and welcome to this session where I wanted quickly to give you a kind of brief introduction to what we are going to do today. So, and as you can see from the plans here, I'm going to give you a quick reminder from last week on entanglement, entropy, and density matrices. And then we are going to dive into a discussion of 1 qubit and 2 qubit gates and how we can realize them, and how this links with project number 1. So there are, as I wrote to you as well, I have some additional material in just a PDF format, gates, but I will also go through that on the whiteboard. The reason why I don't have it in the Jupyter notebook is simply because the rendering of Quant-IK set, it's a package on the LaTeX, which allows you to draw many of these circuits. It's I have some difficulties in rendering in a Jupyter notebook. So that's why you have a separate file here. And that's a demonstration on how you can set up operations of these quantum gates in order to generate the Bell states. And we're going to discuss that. And then we are going to look at very, very simple Hamiltonian, which is the start of project number 1. So some of the material today is actually going to be material which many of you have seen before. But I wanted to bring it back so that we are basically on the same page. So there's a part 1, which I just call a background material. And I just wanted to give you a quick motivation for why the whys and hows of quantum gates. So we mentioned this in the very beginning, that when you do quantum computing, it's pretty common to rewrite the unitary operations on a state. This is essentially what we do. And I'm going to remind you of some of this rather quickly now. And these unitary transformations, they can be represented in terms of operations, which are actually physical operations on a state. And we rewrite them as gates, which do something on the states. And then they represent specific interactions of the system with the environment. And then we write down the physical operations of a unitary operator in terms of a circuit, which then is composed of different gates, which are physical operations. But when we write this in pure theory, these are just mathematical operations on a state, which are then represented by these gates. So in the first set of these notes, you will also find how you link these to respective unitary transformations, and they represent selected physical mechanisms. So the first part is actually a reminder from last week. I wanted quickly to remind you about these technicalities about entanglement, density matrices, and say something about the Schmidt decomposition, which is also used as a technicality to study entanglement. And then we are going to remind ourselves of some of the basics of the solution of Schrödinger's equation in terms of unitary transformations. So this first part, which you see here, is actually meant as background material. I will use slides and just go through it quickly, because I know that many of you have seen it. If you've taken a course in modern quantum mechanics, you have probably heard about the Heisenberg, the Schrödinger, and the interaction picture. And if you took a course in many-body physics, you have seen the same quantities. So that's meant as a kind of reminder, but also to bring us back into what we are actually doing. So if you think of quantum computing, that is an instance of a more generic scheme or theme, which is called quantum control. So quantum control deals with you initializing the system. So like when we are going to generate the Bell states, we are going to start with 2 qubits in the state 0, 0. Then when we have initialized the state, we are going to act on the state with some operators. That's going to represent the time evolution of the system. That's part 2. Then part 3 is then the measurement. So if you think of quantum control, it contains these 3 ingredients: initialization, the time evolution or the evolution of the state, and then a final measurement. So the evolution is where the system gets exposed to some kind of external probe or some interaction. This is in essence the 3 main themes in quantum control, and that enters quantum computing, which is just another instance of quantum control, quantum sensing, etc., etc. So this first part, as you see here, is essentially us reminding ourselves about some basics. And then we are going to look at some of the physical processes. And then in the second part of the second lecture, we're going to look at the gates. And we are going to link this with project number 1 and some simple examples. And these things are going to motivate the introduction of our first algorithm, which is the variational quantum eigensolver, which again is an instance of what we call parameterized quantum circuits, which means that we are going to parameterize the ansatz for the wave function in terms of different rotation matrices and angles. And that leads to an optimization problem. So the VQE is a hybrid algorithm, which is a mix between classical optimization and the quantum implementation. Okay. There are also some notes which I will leave to you, which we can also discuss in the lab sessions about how to use Qiskit. And you can actually access Qiskit, the IBM machines, and then Qiskit is IBM's interface to their quantum computers. So there are instructions. If you go to the, and we come back to that, you will also find that up if you look up here. There is an introduction to Qiskit, and this is something which we will leave to the project work and exercise sessions. But I normally recommend you to take a look at that. The project, which we are coming back to, is a project where we want you to write the code yourself so that you have an understanding of what is going on. And the reason for why we do that is simply because I think that gives you a deeper insight. But you can compare what your code is giving with Qiskit, which allows you to run that on your laptop. Alternatively, you can run it on a real quantum computer and compare what your code is giving with what a real quantum computer is giving. So in the first exercise we have in the project, there is an exercise where you have to implement the Bell states, and you could actually test that on a real IBM machine. And you will see then that you don't get exactly 50% as you should get. And that's simply because there are imperfections on a real quantum computer. And we are coming back to that. Any questions, guys? Okay. So what I'm going to do now is a little bit kind of abuse of slides in the first hour. So I hope you can forgive me for that. Essentially because some of the material is actually material which you may have seen in one context or the other one. So the first thing I just want to do is a reminder from last week. So the next 5 to 10 minutes are just reminders. And then I wanted to introduce this Schmidt decomposition. So there are some basic entities which we discussed last week. And that deals with the spectral decomposition. And then when we have this orthogonal basis, which can be an eigenbasis of A, then we can write the spectral decomposition of an operator. And similarly, an operator which is a function of A is written in this way, can be written in this way. And this is something which leads to the kind of more modern interpretation of quantum mechanics. And the density matrices play an important role in quantum computing. And you will practice that in the project as well. We want you to calculate the density matrix, and we want you to trace out one of the subsystems and figure out whether this is a pure state or a mixed state. So important properties is that the cyclic properties of the traces. And that means that when we look at an expectation value or an operator acting on the density matrix, this corresponds to actually the expectation value. So that's a very compact way of writing the expectation value of a quantum mechanical operator on a given basis, where then this psi outer product with psi is the density matrix. And the density matrix, which we normally write like a row here, is then given, has a spectral decomposition where we have this eigenbasis, and P is just the probabilities of being in one of the specific states. An important aspect is that the trace of the density matrix is 1. The trace squared is 1 if you have a pure state. A pure state can be entangled, or it can just be a product state. And then when you have a mixed state, then the squared density matrix, when you take the trace of that one, that is normally less than 1 and larger than and equal to 0. And it is invariant under unitary transformations, which is a very useful property here. And we are essentially going to look at what we call closed quantum systems, which means that the unitarity is well preserved. As soon as you start losing particles to the environment, you interact with the environment, you can actually have a system which may not be described properly by unitary processes. So with a unitary transformation, you can actually show that the trace, oh, there are some typos here, which I didn't see. Sorry for that. There are always typos. So this trace is actually sums to 1 here. Okay. And then another quantity which we introduced last time is actually the density matrix and the von Neumann entropy. And the von Neumann entropy is the quantum mechanical analog of the classical Shannon entropy. So in the project, when you are going to trace out the density matrix of the subsystem, so when you look at the exercises which you have in the project, there's one about the Bell states, and then we're going to trace out one of the subsystems. So it's a 2-qubit system. And then there is a Hamiltonian, which we have, which is also a 2-qubit system. And there we're also going to trace out the density matrix of one of the subsystems. And then we're going to check whether this density matrix represents a pure state or a mixed state. So these are quantities which we discussed in more detail last week, and which we are going to see again in the project. So the reason why I bring this up, one of the many reasons, is that when we are setting up a quantum circuit, we are going to set up a quantum circuit where we want to entangle the particles. And you will see in project 1, when you're going to implement the variational quantum eigensolver, if you don't have an entangled state, you will get energies which are just wrong. Simply because then the final state which you operate with is just a product state. And that does not take into account correlations between the objects. So entanglement becomes very important when we are setting up a simulation for a quantum mechanical system, or if we're implementing a quantum algorithm. So at the end, we are going to discuss in more detail what is called a parameterized quantum circuit. And you can set up these initializations of the states in many different ways. You will see that in more detail when we come to that. So a way to study entanglement, so this is a small aside, which I'm bringing in here, and I'm going to do it by slides. But one of these ways of analyzing whether a state is entangled or not is something which is called the Schmidt decomposition. And many of you have encountered the singular value decomposition in linear algebra. So this is nothing but an application of the singular value decomposition. So let me show you that. So when you look at the entanglement itself, so let me just ask you guys, is entanglement an observable? Is entanglement an observable? I see somebody's nodding their head, yeah? It's not an observable. So it's a theoretical construction which we can use to analyze a state. Now, experimentally, you can reconstruct the density matrix by counting different contributions to the density matrix. And then, so experimentally, you cannot observe entanglement, but you can reconstruct the density matrix and then study entanglement through that. So the construction which we typically do is via the density matrix. And it's a way for us to say something about how correlated the system is. So entanglement is a type of quantum mechanical correlations where you essentially cannot split the state which you have in terms of simple product states. And entanglement, as you will see when we are solving project number 1, without having an initial state which is entangled, you will not be able to get proper eigenvalues when you simulate a system. For those of you who are going to look at other algorithms in the second project, like quantum Fourier transforms, quantum machine learning algorithms, you will see that without entangling the system, we are not going to get an efficient implementation of a quantum neural network. So this is a key property in quantum computing. It's an essential feature. And when we are going to measure it, there are different ways. So one thing I didn't discuss last week was other measures than the von Neumann entropy. There's something which is called the Rényi entropy. And there are many, many other types of discussing entanglement. So if you're interested in that as a part of project 2, there is a possibility to also study different measures of entanglement. I think that's a very hot topic, a very interesting topic. I like it. I mean, everything which has to do with entropy is something which I like. Statistical mechanics was one of my favorite courses, actually. So the Schmidt decomposition, that allows us to define a pure state in a bipartite Hilbert space, which is composed of system A and B. So this is the quantity which you have, where the amplitudes are real and positive, and they're squared sum to 1. So these are the given amplitudes, and the states which you have, they form an orthonormal basis for systems A and B, respectively, like the qubit 0 and 1, which we have seen before. And the lambda i's, which we are going to get, are the so-called, which we are going to extract here, the so-called Schmidt coefficients of a given rank, and is equal to the number of Schmidt coefficients and is smaller or equal to the minimum dimensionality of system A and system B. So let's just look a little bit more on that. So the proof of that decomposition is actually based on the singular value decomposition algorithm. And to see that, you can assume now that the two, we have two orthonormal basis sets for system A and B, and we're just going to call them I for system A and J for system B. So that means that you can always construct a product state, which is a pure state, in terms of you just doing, these are the tensor products. So please keep in mind that when you read this state, I, A, J, B, it's actually a tensor product, but I am leaving out the tensor product symbol here. But this is just a set of product states, and then the coefficients are just the overlap coefficients. So this is pretty basic. And then they belong to a matrix C, which we normally assume to be a unitary matrix. So if you now assume that the dimensionalities of the two subsystems of B and D are the same, you don't need to assume that, but let's just assume that. So you can have different dimensionalities of the two subsystems. Think of this as qubit 0 and qubit 1 in system A and system B. So the states which we define 0, 0 could be examples of that. So then you can always rewrite that matrix in terms of a singular value decomposition. We know that every matrix can always be singular value decomposed. And the singular value decomposition simply says that you can rewrite that in terms of two orthogonal matrices, U and V. So if they have the same, if it's D and D here, which is a dimensionality, this has dimensionality D times D, and this D times D. And the matrix sigma contains the so-called singular values. So I'm assuming that you guys have seen the singular value decomposition before. And then that means that you can actually rewrite these coefficients C, I, J in terms of the singular value decomposition. So if you look back here, the matrix C is now given by these three matrices. And that means that I can actually rewrite Cij in terms of just a sum over K internal sum here. And then we have the final matrix elements. And then you can insert that in a definition of the pure state, which is given like this. And when you rewrite it, when you insert that one, then you can rewrite it in terms of one basis here, which is now the basis K, this one, for system A, and the basis K for system B. And you simply identify this, since the matrix U and V represent unitary transformations, you can actually represent it in this compact way here. which is what we wanted to show. So this is normally known as the Schmidt decomposition. Now, the thing with the Schmidt decomposition, it's actually straightforward to prove this relation in case systems A and B have different dimensionalities. Once you know the Schmidt decomposition of a state, you can immediately say whether it is entangled or not. If a state is entangled, then its Schmidt decomposition has more than one term. And stated differently, the state is entangled if the so-called Schmidt rank is greater than 1. There's another important property of the Schmidt decomposition, which is related to the properties of the density matrices and their trace operations. And these are concepts which we can study in, which we're going to look at in Project 1, but I'm also going to say something about that next week. So this was just a setup of the Schmidt decomposition without us having used it, and it's meant more as a kind of digression to what we discussed last week. Now, what I want to do now is simply to remind you a little bit of the essential mathematics which we are going to deal with, and which we will rephrase as gates. So this is just a background which many of you have seen before, so I'm going to take the liberty of going a little bit quickly through it on using slides only. But I bring it up here because I think it's something which is useful to be reminded of. So if you look at the Schrödinger equation with its time evolution, we know that a formal solution is then given by us propagating the system to a time t, and we have a unitary transformation. This unitary transformation is the one which then is applied to the system in an initial state at a time t0. Okay, so who has not seen this before? Okay, good. So I hope you can forgive me if I just go quickly through these things, but I just wanted to bring them up because essentially what we are going to do is encompassed in this operation here. So the different gates which you will see, they are represented by unitary operations on a state. So that means that when you look at a quantum circuit, this is going to be represented by a set of sequential operations on a state at given time steps. And every such operation represents a physical process. So it could be a laser acting on your system, prepares it in an excited state, and then you have a new gate which represents another physical process, etc., etc. Okay, so this is actually the basic part, and we know that this Hamiltonian is Hermitian, and then the exponents represents a unitary operator which with an operation carried out on the wave function at the time t0. So since this is unitary, then we have a unitary transformation here which we can write as t at t0, and we would simply write this in a very compact way like that. So the quantum mechanical gates, which we are going to look at, like a Pauli X gate, a Pauli Y, Pauli Z gates, etc., are going then to be represented by this generic operator, U at a time, acting at a time t0, and bringing the state to a new state at a time t. I hope you don't get offended if I remind you of these things. Right? But I just wanted to emphasize that this is the basic mathematics, which we then are going to convert into quantum circuits. And some of you may have encountered the so-called interaction picture. Especially if you took a course in many-body physics, this is something which allows us to make a transformation of these unitary operations. Often, and you will encounter this in Project 1 as well, we can split the Hamiltonian in terms of an operator H0 and an operator Hi, which stands for the interaction. This H0 is often a part of the Hamiltonian, which we can solve, hopefully, analytically. And you will see in Project 1 that H0, for most of the cases, is going to be an operator which has qubit 0 and qubit 1, or many qubit cases as a computational basis, an eigenbasis. So if you think of H0 being a Pauli C matrix, then if you use qubit 0 and qubit 1 for a 1-qubit system, then this H0 will have those states as an eigenbasis. And then we have some additional interaction where these do not commute. So it means that part of the system can actually be expressed in terms of the computational basis which we have, which in our case is given by the different qubits which we have at our disposal. And in general, these do not commute. We know that kinetic energy and potential energy do not commute. So what you want then is to have a unitary transformation in terms of H0. So that's another one, which is widely used. And that leads to the interaction picture. So, which again is a unitary transformation carried out now at the time t on the wave function in the Schrödinger picture. So this defines a new operator and a new state. And you can easily find the equation of motion by taking the time derivative. So if you take the time derivative here of that state, you can rephrase that one in terms of the wave function in the Schrödinger picture. And if you do that, you will simply find that when you massage this equation here, you will then get an equation of motion, which is a lookalike of the Schrödinger equation of motion, or the Schrödinger picture, except that now your unitary transformation is different. So normally what we are going to use in these quantum computing systems is what is normally called the Schrödinger picture. That's the standard approach. But you can also express things with the interaction picture. And then when you look at the expectation values in these different pictures, you know that in the Schrödinger picture, this is the way you would define an expectation value of a given operator. And you can actually show that the expectation values in the different pictures, this I here is for the interaction pictures, they should obviously be the same. I mean, the physics shouldn't change depending on the kind of picture which you're using to express your mathematics and the formalism you want to develop for solving the equations. So sometimes it's easier to work in the interaction picture, and sometimes it's easier to work in the Schrödinger picture. I'm going to skip some of these slides here. One thing which is important is in all these pictures here, this kind of unitary transformation has obviously the value that when you stay at the same time, t0, this transformation has to be equal to 1. This operator here is actually an operator which has the same properties which you expect. It's a unitary operator. We also know that when we start at a time t double prime and you go to time t, this can be brought together into this one. And then we have the unitarity here and also the hermiticity of the operators. So these are some basic properties of these unitary transformations, which I just wanted to remind you of. And I'm not, as I said, I'm not going to go through everything here, but you can actually, in the interaction picture, you can find an expression for this unitary operator, which is given in terms of this integral. And for those of you who have taken a course in quantum field theory or many-body physics, you have probably already encountered this expression here. Does that ring a bell? Something you've seen before? Yeah, I can see somebody nodding here. But this is something which we will not be using. So not everything here is something which I'm going to go through, but you can actually rephrase this one in terms of a time order, where this t is a time ordered series of operations. So where you operate on the system at a time t1, t2, up to a time tn here. There's also another picture, which is called the Heisenberg picture, which is another alternative, so how many of you have encountered this? Is this familiar? Okay. So I hope, as I said, I hope you don't get offended here if I repeat things. This is also handy, especially if you deal with a many-body method like Green's function theory. That is normally expressed in the Heisenberg picture. And in this specific case, we have an OH here, and then we have a slightly different transformation here, but now where we have the full Hamiltonian. One of the advantages here is that the theory, if you truncate things, the theory will always be unitary and obey the variational principle. And then you can do much of the same exercises. And you can find that an operator in the Heisenberg picture is given by this specific transformation, where you have the operator in the Schrödinger picture. And you also find the same equation of motion, but they are slightly different now. So they're given by this commutator between the operator you're looking at and the Hamiltonian of the system. So there are slight differences. And these states here, it turns out that the Heisenberg picture is given by the Schrödinger solution at time t0, which is also equal to the wave function at time t0 for the interaction picture. And this operator again, the unitary operator, which the unitary transformation, you can show that you can transform from the interaction picture at a given time to the Heisenberg picture. So I'm going to skip, I'm not going to bring up everything, but I wanted to say something because in this course, we are going to look at the algorithms mainly. The algorithms for implementing, let's say, a specific set of equations. So in project number 2, if you're interested in solving differential equations on a quantum computer, this is something which is fully possible. However, I think at a certain point, it's also useful to be aware of how these gates are implemented. So this is just a small digression where I just wanted to say something about how we actually implement these gates. And one of the typical systems, one of the actually first prototypes for quantum computer is something which is based on nuclear magnetic resonance. That was one of the proposed approaches for constructing a quantum computer. It uses the spin states of a nucleus within a molecule as qubits. So you can think then of these states of the nuclei, of having specific excited states with a given spin. And then you use these as qubits. And these states are normally probed through nuclear magnetic resonances. This is a very important technique. And the system, and that allows the system to be implemented as a variation of nuclear magnetic resonance spectroscopy. That differs from other implementations in that it uses an ensemble of systems, in this case, molecules. So it's rather, sometimes it can be difficult to prepare the initial states. So there is some background if you're interested in looking at the technology for NMR. So this is one of the quantum platforms, but I mean, the leading quantum platforms now are more based on neural atoms, on superconducting qubits and quantum dot systems. But the essential thing here, just to make it simple, is that, and also the way the different gates appear, if you now consider the Hamiltonian of a nuclear spin in a magnetic field. So the spin provides a magnetic dipole moment, and a nucleus with a spin will interact with a magnetic field. Now, there are some typos here. I have to clean up. I see Hamiltonian. That's a Hamiltonian. And then the Hamiltonian of a nucleus with a spin interacting with a magnetic field is simply given by, and this is probably something you've seen before. So they have mu times b, and this mu is given by the spin, when gamma is the magnetic, this is gyromagnetic factor, and s is the spin. So this is a spin times the magnetic field. And this is one of the simple Hamiltonians which you probably have seen in different courses before. And then it's common to let the spin interact with a constant magnetic field along the z-axis. And that gives us an effective Hamiltonian which simply contains omega L, which is called the Larmor precession frequency. And then you have a Pauli Z matrix, the Pauli Z. So when this acts on a state, if you now go back to these unitary transformations, if you look back a little bit, these unitary transformations we have here, you will now see that if we go a little bit back, let me find the equation, you could now think of this H here as being this operator, which you saw here, this operator here. So you replace that one, and this is what now acts on the systems and evolves the system for us. This is again something which we are going to translate in terms of Pauli Z gates. And then if suppose that the initial state, a 1 qubit state, if you have a spin half state, which is actually used for this kind of NMR studies, suppose that points along some arbitrary axis. And then we know that if we go back to what we did some weeks ago, we can, using the block sphere, we can actually represent the state, a general state on the block sphere. at the time t equals 0 in terms of a cosine theta half plus the sine theta half acting on one axis on qubit 0 and one on qubit 1. Then the next step is actually to let the Hamiltonian evolve. And when you do that, you have this operation here on that state. And when you insert the Bloch sphere ansatz, then you get the state at the time t, which is now given by the Pauli Z matrices acting on this state and the Pauli Z matrix acting on this state. So we're coming back to what this may actually mean for us. The specific Hamiltonian we have chosen here serves to exemplify how we can present physical operation in terms of specific gates. So this sigma c, which you see here, if you now do the exponential expansion of it, this is something you can simplify in terms of just a term with sigma c and a sigma c squared, which is equal to 1. So this expression here actually simplifies. So this kind of long detour was mainly meant to give you a feeling on what these physical operations look like. Okay? And if you look at this state here, you can actually manipulate it further because you have an exponential with an operator A. And we know that when that acts on the state, this is simply given by A of n, which is the eigenvalue of that specific operator, if this A is an eigenbasis. So if you look at sigma z here, this one, and we know that 0 and 1 are eigenstates of sigma 0, then we can actually perform this expansion here because we can then replace the action. So A is either 0, 1. If you look back at this expression which you have here, what we are doing then is simply to rewrite this in terms of the standard exponential expansion. And we know that A acting on A is an operator which just gives us either 0, 1. If A is 0, then we get back 0. And that means that we can rewrite in a compact way like the exponential of the eigenvalue times A. And using that one results in a new state, which you can actually write like this. So that's the new state which we have evolved by the action of that gate. Okay, so now comes the part where I'm going to switch to the whiteboard. And now we're going to look at the type of gates which we typically are going to encounter in this course here. So let's do that before we take a small break. And then this is also where we are going to roughly represent what we are going to look at in this, both in project 1. So let's switch over to the whiteboard. So let me do that. So if we now want to summarize what we have been doing, so let's just write down here, this is a discussion of gates. And we are going to look at the 1 and 2 qubit gates. These are the basic building blocks in basically all quantum computing algorithms. You can make 3 qubit gates or more complicated gates, but these are essentially those which are most used and also those which you can directly link to physical processes easily. So discussion of 1 and 2 qubit gates. So if you think of what we discussed now, so we have some state of the system, and I'm just going to write this with a prime here. This is now given by some unitary transformation times an initial state psi. This is basically what we are going to do when we now write a parameterized quantum circuit in order to run a simulation. So what this means, if we now make a graph here, so we could actually write this in terms of G times psi, and where G stands for gate. So if we now write this in a very schematic way, and we are not emphasizing whether it's a 1 qubit case, 2 qubit case, or many qubit case, we would typically write this now in terms of an operation G, and this ends in the final state psi prime. So the reason why I wanted to bring back a little bit of these definitions of the unitary operations is simply because this is essentially what we end up doing again and again and again. So schematically, this is what we have. Now let's look at how we would trace that G for a simple system. So psi now is going to be first a 1-qubit system. And for the 1-qubit system, we are going to assume a computational basis, which is simply qubit 0 and qubit 1. So let me quickly remind you of that. Computational basis is going to be 0, which is now given by this specific vector, and 1, which is then given by 0 and 1. And this is something which we discussed earlier. We know that the Pauli Z matrix is something which I'm going to label as a Z here. And that is a matrix which is now given by 1, 0, 0, -1. This is an instance of a rotation gate. We also know that the states which we have, 0 and 1, are eigenstates of the Pauli Z matrix. So that means that if I now take this matrix, Z, and act on the state 0, this gives me 0. And if I do Z on the state, just rewrite it in terms of the bracket notation, this gives me minus, so that has eigenvalue -1. We are going to write that as a quantum circuit, which looks like this. So we have a state 0, which comes in. We act on this with a Pauli Z gate, and then we get a state 0 out. Similarly, if we have a state 1, and when I set up these gate operations, I'm not worried about the phase factors. I'm just going to write out the final state 1 here. Okay. Then we have the so-called spin flip gates. If you think of 1 as a spin up and 0 as a spin down state, spin flip gates. And in that case, we have the Pauli X matrix, which is written like this, and that is a 0, 1, 1, 0. And we know that when this acts on the state 0, this gives us the state 1, so it flips the states. And similarly, when it acts on the state 1, it gives us 0. So that means that the gate operation, when we write this as a circuit, a 1-qubit circuit, so these are actually called 1-qubit circuits, what you see here. In that specific case, what you would then have is a state 0. You act on with the gate, and then you get a state 1. So in electronics, this gate has a famous name. Does anyone remember that from standard electronics? Yeah, that's a NOT gate. So this is just the quantum mechanical implementation of a NOT gate. And just for the sake of completeness, I'm going to set up the Y gate, or the Y matrix, Y here. And then we take a small break. So this is simply given by 0, -I, and 0. And then we know that when we have a Y operator acting on the state 0, that gives me I of 1. So that's also a spin flip gate. And similarly, if I act with this one, I get -I of 0. So the X and the Y gates are spin flip gates. I can make a linear combination of X and Y and find a new eigenbasis. And you may remember we discussed that in the very beginning. But the standard basic approach is to assume that qubit 0 and qubit 1 are your computational states. And that means that when we are going to make measurements, we would like to make a measurement in terms of the Pauli Z matrix, because that will act on a computational basis, unless we define another computational basis, which could be an eigenbasis of a linear combination of Pauli X and Pauli Y. Okay, so after the break, we are going to list some other famous gates, the rotation gates, phase gates, etc., which we are going to see in different applications pretty soon. And then we are going to define 2-qubit gates, the so-called controlled NOT gates. And with that, we are going to make our first state, which is a Bell state, using these basic gates. And this is what you need to implement in the first exercise in project number 1. So we're going to go through that. And after that, we are going to look at a 1-qubit Hamiltonian and how we can take and rewrite the standard Hamiltonian in terms of Pauli X, Pauli Y, and Pauli Z matrices. And we are going to end the next lecture by looking at how we can solve that with a parameterized quantum circuit. So that will serve as a kind of preliminary step towards the variational quantum eigensolver. And then it will be more clear to everybody what a parameterized quantum circuit actually is. Should we take a small break, everybody? So I'm just going to put the recording off, just pause it. I also wanted to say one thing in connection with the first exercise in project 1 on the measurements or the Bell states. So in the lectures last week, there is an explicit example. If you go into the PDF file or the Jupyter notebook, you will find an explicit example on where we calculate the expectation value on one of the qubits. And this is essentially you looking back at these lecture notes and implement that numerically. So in the first exercise, we are not asking you to compare that with Qiskit or implement it on an IBM machine. But if you want to try that, I mean, feel free to do so. So in the first project, we want you, as I said, to write everything from scratch yourself. But then in the second project, in order to be efficient and actually be able to implement more complicated algorithms, we will normally recommend to use libraries like Qiskit or PennyLane, or if you're using QBraid or other ones, feel free to do that. The nice thing with Qiskit is that then you can run on an actual quantum computer. And you have a free access to, for instance, the IBM 127 qubit machines. So if you want to test the measurement on a Bell state on an IBM machine, you can actually do that. And there's a recipe on how you get an account and how you start running on an IBM machine. And so if you look at the Jupyter notebooks for this week, there is one explicit, which is just called Qiskit Jupyter notebook. Just take a look at that, because that contains a set of instructions which we will more discuss during the lab sessions. So I won't discuss, I mean, in the lectures, I will not discuss how to run on a specific setup. This is something which we leave to the exercise sessions and the lab sessions. Okay, so what I want to do now is to continue a little bit along these lines and simply remind you of some of the other gates which we're going to look at. So there is a rotation gate, which we will encounter in particular when we are going to derive the quantum Fourier transform. And this has a subscript k because this is a gate which looks like this. So it's a 1, 0, 0. And then it goes e of I of 2 pi divided by 2 to the power of k. Now, for some specific values of k, there are some gates which even have gotten their own name. And one is the so-called phase gate. And you can see now if you have an angle pi half, then this number here, if you now take k equal to 2 here, then you get I, now e with the I times pi half as an argument, and that is called a phase gate. So or just the S gate. So that's a special instance of that rotation gate, and it looks like this, 0 and I. And you know that I is the same as e to the I of pi divided by 2. So that would be an instance of this rotation gate where k is equal to 2. Now, as a quick reminder, I also wanted to remind you, quick reminder, about a state on the block sphere of state. And we had the expression in the lecture notes in the previous hour. You have it in the slides, but I just wanted to remind you of that of state. This is a 1 qubit state on the block sphere. So this would be a general state. It's not 0 or 1. So we would have a state, this is still a 1 qubit state. So we have the angles theta half multiplied with qubit 0 plus E of I. So the angle phi disappears when we are calculating expectation values. So that will be a global phase. And then multiply with 1. Now, the reason why I bring this back again is simply because we are going to look at these angles, which you see here, as parameters when we are going to initialize the system. And then we are going to have an optimization algorithm, which we will discuss next week, which is the variational quantum eigensolver, where we are going to vary the angles, and then we're going to find the expression for the energy in terms of these angles. So the whole recipe is now, if you think of this state here, this is a general state on the block sphere. And it could be the solution to a specific Hamiltonian. So these states which you have here, these are the eigenstates of the Pauli Z matrix. But if you have a Hamiltonian, which is a mixture of Pauli X and Pauli Z and Pauli Y, then this will be a general state whose angles we have to find. So this is, I mentioned this because I want to anticipate the variational quantum eigensolver, which we will discuss in detail next week. Okay, so that was just a small aside. There is another very important gate, which we need to discuss, and that's another qubit, 1 qubit gate, but it can also be a many qubit gate. So you can actually have replica of this for 2 qubits, 3 qubits, etc. And this is the Hadamard gate. And I'm going to label that with an H like this. And this is given by the following matrix, 1, 1, 1, and -1. It has the properties, and you see now that this has real entries, so it is an orthogonal matrix. And it's easy to see that if you just perform these operations, which also means that H of minus the inverse is actually equal to H. You can write this matrix as a linear combination of a Pauli X and a Pauli Z matrix. And you can see that if you combine the Pauli X and the Pauli Z, this is what it gives you. There is another relation which is very important for us, and that is that if I take Hadamard times the Pauli X, so this is not multiplied, this is the Pauli X matrix, this is equal to the Pauli Z matrix. So I'm going to show you that in just a few moments. But there is another relation, because now if you see these, if you use these properties here, I can multiply from both sides with the H minus 1, which is the same as H. So if I multiply H with H here, I get back 1. Then I get H here, and then I multiply with H from the right. So then I can actually get H times H, and that gives me a new relation, so that the Pauli X matrix is actually given by the Pauli Z with 2 Hadamards. Now, there's a reason why I'm bringing in these, and you will see why a little bit later. Because when we are going to make measurements, we are going to make measurements in the computational basis. But your Hamiltonian can contain a poly X matrix. So that means that when you make a measurement, then the computational basis 0 and 1 qubits is not an eigenbasis of this one. But if I rewrite it like this, then I can perform the measurement with this Z matrix here. So it's pretty common then when you're performing measurements at the end, because when we are going to set up everything, we are going to have a superposition of states, entangled states. And then when we perform a measurement, the system collapses to one of the possibilities. And the measurements which you're going to do with the belt states means that you are just going to rerun your code a given number of times. And then you simply collect the number of times you get qubit 0 and qubit 1. And that is your final expectation value. We are coming back to this next week in more detail, but this is also relevant for the first exercise in project number 1, when you do the belt states. So normally you call a measurement, this is a kind of jargon in the field, it's called a shot. So when I say measurement, this is also synonymous with a shot. Okay, so we also have some other operations which are useful to look at, but let's now look at this this Hadamard with a poly X with this one. So when we set it up, this is the same as 1 over square root of 2. It's a poly X plus a poly Z multiplied with a poly X. And then we have a poly X plus a poly Z multiplied with 1 over square root of 2 here. So if I do these operations, if I write everything out here, I'm going to get 1/2. And then I'm going to get the poly X squared plus times X plus a poly X squared times Z plus a Z times a poly X squared. And then I have plus a Z times X times Z, like this. Now, this one and this one and this one, they have a specific value. Anyone remembers that? When I square these poly matrices? Identity. So that means I have an identity here. I get an identity here. I get an identity here. Now, this quantity which you have here, Z times X times Z, you can easily see now, if you now do the algebra, that this is actually minus X. So what you see then, when you bring everything together, is that this term cancels this term. And then we are simply left with 1/2 of poly Z times 2. So that's simply a poly Z matrix. So that's just one way of showing that. For the other relations, I simply invite you just to try them out. So you can also rewrite a Hadamard times a poly Y times a Hadamard. This is the same as a minus Y, which is also equal to X times Y times X. So one of the reasons why we are looking at those relations is simply because we want to perform operations of measurements on the computational basis states. So I'm going to list some of the 2-qubit gates, which are some of the more popular ones, which we are going to study. So these are the 2-qubit gates. There are more than those which I'm showing you here, but these are some of the more popular ones. So we have the so-called control gates. And I'm just going to use an acronym for CU, control unitary. And what this does, and there is a particular gate which we are going to look at. So we have a CU. The standard approach is that we have a qubit 0. So that's for the first qubit. And this is now given by a tensor product of a unitary matrix, which is 2 by 2. This is a 2-qubit gate. And then we have a qubit 1 for the first qubit. And this contains now the specific matrix, which is a U times 2 by 2 matrix. And the general structure is given by a matrix which looks like this. So we have 0, 1. So the first qubit is unaffected. So we don't do anything with the first qubit. And then we have 0, 0, and then we have U0, 0, U0, 1, U1, 0, and U1, 1. And now we're going to look at specific examples of how these matrices look like. So one of the more popular one is called the C0 or the CX gate. And this is simply given as the poly X matrix here. And then you simply have an identity matrix here. So let's see what that is doing on a specific 2-qubit state. So if we now take the C0, which is also written as a CX gate, and if you want to be more picky, it's normally written as a CX 0, 1, and you will see that from the matrix. So then this matrix, the CX, is given by 1, 0, 0, 1. So this is the identity block. I write zeros here, and then you have 0, 1, 1, 0. And if we now look at the product state, yeah.
We physically implement the control gate.
How we physically implement it. Yeah, because then what you would have would be something which contains a poly X matrix, which then would act on the second qubit. And that poly X could actually be some kind of laser pulse, which you would implement. If you think of that case which we had with the, so you're not limited to poly X, you can now control Y. If you take a control Z gate, then you would have a poly Z matrix here. And that could be you acting on the second qubit with a magnetic field. So suppose now you do you have a system like this, and you have one electron here and one electron there. And then you act only on this one with a magnetic field. So this could be system A, and this could be system B. So then you have some B times some sigma C acting entirely on that particle. So if these are isolated and distinguishable systems, and when you act with a magnetic field, you can actually flip the spin here. This is actually used in quantum sensing for measuring a magnetic field. Because what you could have then, you could prepare your state as a singlet state, spin up and spin down. Then when you act with a magnetic field in this system, then you can get a contamination by the spin flip, which gives you a triplet state. So the kind of flow from a singlet state to a triplet state is something you can measure. And from the phases which you measure, you can then extract the information about the magnitude of the magnetic field. So this is actually something which people are thinking of implementing at CERN as a way to increase the sensitivity of detectors, because if you have an entangled state, like you would have here, then you can actually show mathematically that you can increase the sensitivity of a sensor. This is something we can discuss also in more detail. So that would be a typical example of how you would implement a control C gate, where you act on only one of the qubits with a magnetic field. But let's just go back to just the plain mathematics and see what this is doing for us mathematically. So if you now look at this CX gate, if we take the CX gate and act on 0, 0, this is the same as setting up 1, 0, 0, 1. I put zeros here, and then I have 0, 1, 1, 0. And I act on the state, which is the 0, 0 state, which is the tensor product of qubit 0 and qubit 0 in the two systems. So if you look at this one, what would you expect that this gives you? Anyone sees the mathematics immediately? Yeah. Yeah, that gives us 0, 0. So you see now that so this gives us zone like this, and that is just 0, 0. Now what you see here is that we have singled out one piece. So this is the piece which acts on the first qubit. And since you just have an identity matrix, it doesn't do anything. So this acts on qubit 1, whereas this piece acts on qubit 2. And since the non-diagonal parts are 0, then there is no link between qubit 1 and qubit 0. So we normally call this for a control qubit, and the one here for just a target qubit. So what you see now is the following. So let's just act on a CX with a 1, 0. So that means that the control qubit is in state 1. So let me just write the matrix, and then so we have 0 and 0 and 0, 1, 1, 0. And this is now acting on 0, 1, 0, 0. So what happens in this case? Anyone who's, yeah, 1, 1. So this now changes the target qubit to a 1, 1. And I'm going to set up the remaining ones. So if I act with this one on 0, 1, that obviously gives just back 0 and 1, the same state. And then finally, if I act with on this on 1, 1, this gives me simply 1, 0. So what I'm doing now is that if the control qubit is 0, nothing happens. If the control qubit is 1, then something may happen on the second qubit. So this is a gate which now is going to use to entangle a state. So I'm going to show you how you can create a Bell state by you initializing the system in this state here only. But before we do that, let's just bring in another gate, which is also very interesting, which we're coming back to, and that's called the swap gate. And the swap gate is so that when it acts on qubit X and Y, it simply interchanges Y and X here. Yeah.
One more question about the physical implementation.
Yeah.
Because we have to basically check the state of the first qubit to know if the second one
Yeah.
is or not. But how do we implement the checking of the first to know which one to use the second?
Now then you simply have to do the measurement.
Yeah.
And then the state will collapse to either that state or that state. That's the only way you can check it, by performing the measurement. And this is what you will actually do in the first exercise in project 1, to perform the measurement on a Bell state. So the swap gate, when you set it up here, and now after that one, I'm going to look at the example of, so this looks like this, and then we have 0, 0, 1, 0, 0, 1, 0, 0. So this is just one of the examples. And this is a very popular gate, which is also used in entangling states. So when we now are going to look at the Bell states, and this is given in these additional states, these additional slides. So how do we make them? How do we make them? Starting with an initial state, which we can prepare the system in. So suppose now that we start with the state 0, 0. And this is a very typical situation because you could think of, again, to use this example with trapped electrons, which is in a case of a quantum platform called quantum dots. So you could think of you being able to prepare the system with an electron with spin down here and an electron with spin down here. And you would label that as 0 and 0. So suppose this is the lowest lying state of the system. And then we know that the state is initialized in that specific state. And now I want to create an excited state, which is given by a Bell state. So you could initialize the system here, and then you're asking yourself, suppose now that I want to initialize my system in an entangled state. So what do I do then? Now, one thing which you need to do is to perform first a superposition. So let me just remind you of the Bell states. So we have one of the Bell states is a state which is given by 0, 0 plus 1, 1. And we have 3 more states. So in these additional slides, you will find how you can actually make a psi minus, psi plus, and psi minus Bell state by acting with different gates. So let's now look at the operation on this. So what we want now is 0, 0. And then we are going to send this one through some gates, which I just write like a G here. And this gives me, at the end, phi plus. So this is basically what we're going to do now. And we are going to write this as a 2-qubit system. So the state 0, 0 is actually a 2-qubit state. So the first thing which I'm going to do now is to act with a Hadamard gate on the first qubit, because I need to make a superposition. In order to get a superposition of 0 and 1 here, I would actually need to perform a Hadamard on the first qubit. So what we do now is a Hadamard on the first qubit. So what it means then is that we are now going to set up qubit 0, that's the first qubit, and we perform a Hadamard like this. And the second qubit is unaffected by the Hadamard operation. So if we do that, so remember now that if I act with a Hadamard on one of the qubits, 0, this gives me 1/2, 1 over square root of 2, of 0 plus 1. So the Hadamard gate, when we are going to discuss quantum circuits, is actually one of the basic operations which we do on the system in order to get a superposition automatically. So that's the first step, which we normally always would do. Then the next thing, which we are going to do now, so that means that our state, when we act on this Hadamard, and then we have the identity on the second qubit, on 0, 0, that is going to give us 1 over square root of 2 of 0 plus 1, and then tensor product with 0, which is our second system. That sound reasonable? Then that means that what I have, so this gives me 1 over square root of 2, and then I have a state 0, 0, plus the state 1, 0. Like that. The next thing I'm going to do now is to take this state, so which I'm going to call phi prime. So that's my first operation on the system. In the next step, what I'm going to do now is to take a Cx and multiply that with that state. And that is going to be my final state. And then we're going to see what this final state looks like. So this means that what I'm going to do now is simply to perform the operation with the 1, 0, 0, 1. We have zeros here, and then we have 0, 1, 1, 0. And this is going to be multiplied with, and then I have 1, 0, 0, 0, plus 0, 1, 0, 0. Now, what happens is that we know that when this Cx acts on the state 0, 0, that gives us simply 0, 0, as we saw before. And when Cx acts on 1, 0, this gives us simply 1, 1. So my state psi prime, double prime here, is now going to be given by 1 over square root of 2. And then I have 0, 0 plus 1, 1. And that is one of the Bell states, which we discussed last week. So we have now an entangled state. So keep that in mind, that the state which you see here is an entangled state. And when we produced the density matrix last week, and we traced out one of the sub-density matrices and calculated the von Neumann entropy, then what we saw last week is that this state is a so-called mixed state. That means that when we trace out one of the density matrices for the subsystems, we will find that the system is in a superposition of state 0 and state 1. So we cannot tell, even though in the beginning, we actually had a state, which was a pure state, but it is entangled. So remember that a pure state is a state which you can define exactly when you start doing the simulations. But the state is still entangled, as we have been discussing. But it's also when we trace out, the subsystem is a mixed state where we cannot define whether we are in state 0 or state 1. And that means that the entropy is no longer 0, but it's actually an entropy which reflects the undeterminedness of the system. Okay? So these are things which you will essentially practice in the first exercise of the project. So if we now set up a graph here, what this looks like is as following. So the circuit, in terms of a graph, is actually something which we now will write like this. So the first qubit, we do a Hadamard. We don't do anything on the second one, but you could have done a Hadamard on that one as well. And you will typically see that that is a pretty common recipe when you're setting up a parameterized quantum circuit. In the sense that if you do a Hadamard on both of them, you will have a superposition for both qubits. Then this produces this state here, which we call psi prime. The next operation which we have is now the so-called control X gate. And this is normally written like this. So now we have a 2-qubit gate, and that produces the final state here, which in our case is just one of the Bell states. Now, in those additional slides, which you have for this week, there is also an example on how you can, starting from this state here, which is often easier to prepare the system by assuming that both isolated systems are in their initial states. Then there are examples on how you can, from this state here, and different combinations of poly X, poly Y, Hadamards, and C NOT gates can actually reach the other Bell states. So take a look at those, but this is essentially the message which we are going to, or rather what we are going to use in many of the implementations. So this produces an entangled state. And when we are going to diagonalize a many-body system, the states are normally entangled. There are quantum mechanical correlations. So the whole concept of a parameterized quantum circuit is normally that we will perform rotations here. There will be angles, which then will prepare the system in a given state. That state is hopefully something which expresses all the correlations we have in the system. And then we are going to optimize that state and the expectation value of that state in terms of the parameters, which are the angles. Okay? So let's try to look at this in the Jupyter notebook and how we are going to look at the exercise B and rewrite a 1-qubit Hamiltonian in terms of poly X and poly Y matrices, and how we can start our first calculation and our first basic stupid approach to the variation of quantum eigensolver. Okay? So I'm going to switch to the Jupyter notebook. Any questions to this? So I invite you to take a look at how you construct the other states. And this is something which, together with the lectures from last week, hopefully gives you a kind of entry for solving the first exercise. Yeah. Could you say it again? Because yeah, exactly. Yep. So different combinations of poly X, poly Y, Hadamards, and control X gates will give you all the other Bell states. Yeah. Yeah. Absolutely. Yeah. So the whole thing is that if you think back of what I mentioned as a kind of overarching elements in quantum control, initialization, evolution of the system, measurement. What you could do now is you initialize the system evolves to an entangled state, and then you perform a measurement. And when you perform the measurement, you would typically perform the measurement on one of the qubits, or you could perform the measurement on both qubits. And then you do these measurements again and again. So actually on a quantum computer, you're running these kind of experiments many times. And one of the options when you run on the IBM machines is simply to specify the number of measurements, which is normally called the number of shots. And then what you do is you invoke Bernoulli's law of large numbers, and you hope that when you've done many enough measurements, that you will get, like in this state, if I now measure on one of the qubits, I should get 50%. If you go back to the lectures from last week. And this is what you will see in exercise 1 of the project. Okay? Any questions? So what I want to do now is just to bring up our first approach to the variation of quantum eigensolver. And this is exercise B in the project. So let's now take a closer look here at the Jupyter notebook. Too many windows up here. So if you scroll down to basically the end of this week's Jupyter notebook, what you will find then, so let's just scroll down here. What you will find is a simple 1-qubit Hamiltonian. And let's just, so you will basically find many of the same things which we've been discussing till now. So this is where we will start. We are now looking at a system which represents, which has as a computational basis qubit 0 and qubit 1. Now, we are going to let the Hamiltonian be composed of one part, which is diagonal. And this part here is the one which have qubit 0 and qubit 1 as eigenstates. Okay? So that means that I can now expand later my solution as a linear combination of qubit 0 and qubit 1. So if I have qubit 0 and qubit 1 as an eigenbasis for this 2x2 matrix, I only need two states, right? So this is qubit 0 and qubit 1. These are matrix elements of a Hamiltonian. When I diagonalize, I know I have only two eigenvectors. It's a 2x2 matrix. And that means that if this H0 has 0 and 1 as an eigenbasis, then the final problem will be given by a linear combination of qubit 0 and qubit 1. Does that sound okay? So many of you have seen this when you did many-body physics. So what we are going to do then is simply, instead of diagonalizing this, and this is a kind of baby case, because you can diagonalize by hand here, and get the eigenvalues immediately if you have the values for the interaction and this E1 and E2. Okay? So when you're going to compare your first approach with a quantum eigensolver, you can compare that one to the exact diagonalization. So what we have done then is simply to assume that this operator H0 has qubit 0 and qubit 1 as eigenstates. This is essentially a repeat of what I said. So where we have defined the orthogonal computational 1-qubit basis in terms of these two guys here. Now, what we do now is a simple rewrite of the Hamiltonian in terms of poly X and poly Y. And you know that if you look at this Hamiltonian, which you have here, this here could be, the diagonal could be given by a poly Z times some constants. And the non-diagonal ones could be given by a poly X times some constants. And if you just scroll down here, you will now see that if I just introduce this trick here, where I have this epsilon, which is E1 plus E2, and this omega as E1 minus E2, if I bring these together, I can actually rewrite the H0 part, the diagonal, in terms of a diagonal matrix plus a Pauli Z matrix. That's first step. Then I can take the interaction by simply manipulating the diagonal terms of the interaction and the non-diagonal ones. And then I can rewrite the Hamiltonian in terms of a Pauli C, Pauli X, and an identity matrix. So that's the Hamiltonian. So one useful test to see that everything is running correctly is actually to, one, diagonalize this Hamiltonian, which you have here, and then diagonalize the one you have rewritten in terms of Pauli X and Pauli Y matrices. Now, this is something which actually is at the root of everything we do here. Now, there are some specific Hamiltonians, and some of you have encountered the Ising model. So who has seen the Ising model? Heisenberg, Hubbard, so on. These are models which are written in terms of spin matrices. So that means that my Hamiltonian is ready for quantum computations because it's already written in terms of Pauli matrices. And remember now that we are making the measurement in the basis of the Pauli Z matrices. So we measure in the computational basis. So that means again that we would like to transform a given Hamiltonian, which can look pretty complicated in terms of Pauli X, Pauli Y, and C matrices. This is called, if you use second quantization, which some of you are familiar with, that is something which is called the Jordan-Wigner transformation. So you can transform a Hamiltonian, a general one, into a combination of Pauli X, Pauli Y, and Pauli Z matrices. The Hamiltonian which we are going to look at is something which some of you already have encountered, the so-called Lipkin Hamiltonian, because that can be rewritten in terms of quasi-spins, which then can be interpreted as spin operators. So that means that the transformation of the Hamiltonian in that case is a little bit simpler. But if you have a general Hamiltonian, you would have to have linear combinations of several Pauli X, Y, and Z matrices, which then complicates the calculations. So the length for the circuit is given by the number of matrices you have to, operations you have to do. So the more complicated your Hamiltonian, the more operations you need to do. And that can easily be affected by decoherence and noise, etc., etc. But essentially what we do is this. Now, what we can do next, so here I've just selected the parameters. This is just an example, and this is the exact eigenvalue. And then there's a test where I just rewrite everything. So this can aid you in exercise B of the project. So if you look at this example, it's essentially one of the things we want you to do there. And you can see now that I'm just setting up the Pauli X, Y, C matrix, the identity matrix, and I'm simply setting up the Hamiltonian. And as a check, I've actually computed the eigenvalue, and that should be equal to the one I did when I diagonalized the matrix, right? That shouldn't come as a surprise. It's just a rewrite of the Hamiltonian. And that's a kind of sanity check. But then, where do we want to go now? So keep in mind, this is a 1-qubit case. So let me just quickly go back to the whiteboard. And I hope I can sneak in some 5 minutes here, if that is okay with everybody, because I wanted to stop there. But let me just bring back the whiteboard quickly. So in the whiteboard, what we did was to remind ourselves about the state, a general state on the block sphere. So the state which you see here. So that means now that my general state, 1 qubit, is actually the most general expression is given by this state on the block sphere. However, for that specific Hamiltonian, I don't know which angle theta and pi are those which correspond to the eigenvalues of the system which now has this non-diagonal matrix. Okay? Everybody sees that? So what can we do then? And this is a kind of teaser for what is coming next week when we discuss the variation of quantum eigensolver. So let me bring back that one, and this is where we end this week. So what I'm going to do now, since I have only 2 qubits, not 1 qubit, I'm going to make an ansatz where I perform a rotation along the x-axis and the y-axis. So these angles, pi and theta, they become parameters. Okay? And what I want to do then is to find the angles which give me the exact eigenvalue. So then what I do with this guy here, this one, so I'm having a qubit gate for rotation on x and a qubit gate on rotation on y, and we are coming back to that next week. And then I calculate this expectation value. And then I perform the measurement in the basis of z. So these are the typical rotation operators which I'm going to implement. And there's a code example here, which we're coming back to, so you can see the implementation. Now I'm just fixing the angles. So I just give 2 random values. I just pick them randomly here. So theta of pi half and 0.2 times pi, okay? Just 2 values I just picked on the fly. These are the rotations. This is my original basis. This is my computational basis. The new basis is now ry times rx times the basis. And then I take the new basis. I obviously have to do the conjugation properly, because else you would just get wrong results. You would get an imaginary component, which is non-zero. So just pay attention to that. I multiply with the Hamiltonian and just calculate what you see here. And if I do that, so I print the new basis, and then I print the eigenvalue. And remember the eigenvalue, the exact one, was here, 0.98. And here you see that I get 2. So that's not very impressive, right? So the angles are not the correct ones. So what I'm doing next now, I insist on this brute force way. So there's no optimization. So now I pick randomly 20 values for the angles. And what I do then, I pick the angles, I perform the Rx, I do the Ry transformation, and then I calculate the new basis, and I simply calculate the expectation value, and then I calculate the difference between the exact one and this expectation value. So this is still very brute force, but you see now that I actually pick one which has a very small difference. So what this is me anticipating a variational procedure where we are going to perform an optimization where we calculate the gradients of the energy as a function of these angles. And then we're going to optimize that. Okay? So you see where we're going? So we're going to have a hybrid situation where the rotations and everything is done by the quantum computer. We get an energy expression, which we then feed into a classical optimization algorithm. And then that gives us angles back. We rotate again in the y and x direction. And then we keep going till the gradient is 0. So next week, we are going to extend the above 1 qubit to a 2 qubit problem and analyze how we can set it up. So that's exercise D. And we are going to discuss the quantum eigensolver, or the variational quantum eigensolver for the Hamiltonian system. That's essentially the first 4 parts of the project. And next week, we will discuss this as part of the exercises, and we will discuss the variational quantum eigensolver. So there are also some additional exercises you can look at here and how you rewrite the Hamiltonian, and also some measurement basis here. I went a little bit over time, but I wanted to give you this kind of teaser so that you know where we are heading next week. So now we did everything brute force, but essentially we have the exact state, which is somewhere on the Bloch sphere for 1 qubit. And then we want to find the angles. Does that sound okay? Good. Next week, variational quantum eigensolver. And that gives us a parameterized quantum circuit, because the circuit is parameterized in terms of the angles. Okay, guys. See you next. See you.